All right, so our purpose here really is to look at a couple of real chemical changes, chemical reactions, and write balanced chemical equations. So the idea with a balanced chemical equation is we want to follow the law of conservation of mass, which says if you have some sample that's going to undergo a chemical change and the chemical change happens, the atoms that you started with are still present afterward. They may have had chemical bonds break and new chemical bonds form, but the atoms that you have are just rearranged into new compounds. And that's the idea behind a balanced chemical equation. So for this reaction, we've actually seen reaction number 1 in the zinc chloride empirical formula lab, but I'm going to do it in a slightly different way that will help us produce more hydrogen gas. Because what we want to do in reaction 2 is have enough hydrogen gas collected that we can ignite it. Hydrogen gas is flammable, and we want to observe that as well. Okay. So let me turn on the camera here. I want to show you the form of the zinc that we're using is different. So we're not going to use zinc sheets. We are using something called Mossy Zinc, which is kind of these randomly shaped pieces of zinc. And the way that this is actually produced is if you take molten zinc and drop it into water, it kind of hits the water, splashes in, and just solidifies into all these sorts of different random shapes. And it's good for this reaction because you've got a lot of surface area that the acid can react with to make the hydrogen gas. So this is what we'll be reacting inside an Erlenmeyer flask. The other difference is we're going to use an acid with a higher molarity, so a higher concentration. That'll make the reaction go a little bit more quicker, and will produce more hydrogen gas as well. So let me get this set up, and I'll keep my camera going here so you can see the reaction. So I'll set this up on this stand just so it's a little bit higher for you. And I need to grab my Erlenmeyer flask. And I've got this black base here just because it gives a little bit more contrast for you to be able to see what's going on with the reaction. So I will take a couple pieces of Mossy Zinc. That should do. All right, so we'll be able to see that close up. I'll get goggles on in a second. The other thing that I'm going to do just to be extra safe is I've got a safety shield here, and because hydrogen gas is flammable and can be explosive, I like to just take that extra precaution. I actually did have once hydrogen gas explode while I was doing a demonstration when I didn't expect it to, and it was really loud and it really surprised me, and somehow I had my goggles on. Somehow, some way, I didn't get splashed. It was a different reaction, so it was actually using water and lithium. We saw that earlier in the year where the little lithium kind of speeds around on the water. I was collecting it with a test tube, and it must have sparked, and it must have been just in the right concentration to go boom. And it was big enough that like it splashed up to the ceiling, and like I was standing right there, and I somehow didn't get splashed. But ever since then, if I'm using hydrogen in a demonstration, I use a safety shield just to be extra careful. All right. Okay, let me grab my goggles. So on your sheet, the reaction is between solid zinc and hydrochloric acid. So here's my HCl. I don't really need to be exact. I need about 50 milliliters. And pretty quickly, if you look on the screen, you can see it's bubbling quite a bit. It's a pretty rapid reaction. It will only get faster as kind of the zinc oxide coating gets kind of dissolved away from with the acid. And I want to collect the gas. So I'll put a funnel on top. See that? And I'll bring over a test tube stand for my test tube. Lower that down just a little bit. So the idea is the hydrogen gas is less dense than air, so it's going to rise. It's going to be directed through the funnel here into the test tube. And I've found that about 5 minutes is a good amount of time to get good ignition quantity. So I'll get that going on my watch here. And we'll go ahead and look at what the balanced equation looks like. Move this back because this has my microphone. All right, so we need to show what's going on in the reaction, both symbolically, and we're going to do it in a diagram as well. Okay, so we've got solid zinc. Come on. Oh, there it is. It froze on me for a second. Come on. There we go. All right, so solid zinc is just zinc, Zn. In parentheses, we'll put S for solid since it's specified in the equation. We can do that. And it's going to react with aqueous hydrochloric acid. And it tells us the formula of hydrochloric acid is HCl. I'm going to put AQ for aqueous. And what that means is the hydrochloric acid is dissolved in water. And we'll talk more about that in a moment. Our product is hydrogen gas. That's what's going to ignite, hopefully, on step 2. And aqueous zinc chloride. So we did this lab, we did the empirical formula, and we found that the formula is ZnCl2. And it is also aqueous, so it's dissolved in water in the end. Okay, so if we were to draw a picture of what's going on kind of on the atomic level, I'm going to represent zinc as zinc in a circle. The circle is just representing an atom of zinc. I want to do the same for HCl, but I'm going to draw it a little bit differently because it's aqueous. So one thing about acids is when they dissolve in water, they almost all of them produce an H+ ion and a leftover negative ion. So HCl as a molecule is actually covalently bound, but when it's aqueous and dissolved in water, we have hydrogen ions. So I'm going to put H+, and it's still an atom. It's just a charged atom of hydrogen. It separates and mixes in with water separately from the chloride ion, which is Cl-. So I'm going to represent that not as like a stuck together HCl molecule, but a separated HCl aqueous solution. So what I'm going to produce in the reaction is hydrogen gas. There's a reminder here that hydrogen is diatomic. A hydrogen atom has one valence electron. It's very unstable. If it joins up with a second hydrogen atom, it can make a single bond, and the molecule is quite stable. So H2, I'm going to represent as a hydrogen atom stuck to a second hydrogen atom. And then the zinc chloride is aqueous, and this is an ionic compound. It gives us a reminder that zinc is always a +2 ion. So again, because it's aqueous, I'm going to draw a zinc +2 ion separate from 2 chloride ions, 2 different Cl- ions. So the idea behind balanced chemical equations is that whatever atoms you start with, you end with none left over. And if I look at how things are right now, I'm unbalanced because I have a hydrogen atom here. It happens to be charged. I've got 2 hydrogen atoms here, and my 5-minute timer just went off, so I'll do step 2 here pretty quickly. I need to have 2 hydrogen atoms on the left-hand side of the equation if I end with 2. The only way you can change the equation is multiply formulas in their entirety. I can't just add a 2 here because that's not it's not hydrochloric acid anymore. I can only multiply the entire unit. So if I put a 2 there, what I've done essentially is added in a second pair of HCl ions. And now I can imagine those 2 hydrogen coming together to make the H2 molecule. The zinc is still over here. A 1-to-1, 1 zinc became a zinc ion. It's still a zinc atom, it's just carrying a charge. And my 2 chlorides are still hanging out here in the ZnCl2 aqueous. So this is the balanced chemical equation. And although we don't normally write it, we are implying that there's a 1 here, a 1 here, and a 1 here. Okay, so that's the balanced equation for the first reaction. So I'll go with my camera back over to the test tube, and now we should have collected enough hydrogen that we can ignite it and see what that looks like. Let me see if I can kind of get a picture of the whole thing here. So I'm going to remove the funnel. It's still bubbling away pretty good. And the best way to light this is with a wooden splint. So it's just a thin piece of wood that I can light. And I'll bring the flame to the bottom of the test tube, and it should ignite the hydrogen. There it is. Okay, so it's a really rapid explosion, and the gases expand, and you get a pretty quick pop. All right, so that's kind of a classic hydrogen test. Now, if we look further down on our sheet, one of the products of the reaction, actually the only product of the reaction, is water vapor, and it didn't make a lot, but maybe you can see it on the screen, maybe not. My hand behind it, maybe. And it's not going to focus, is it? But I can see some water, some moisture in the test tube that came from that water vapor that was formed. Okay. So we'll look at the second equation next. And I also want to show you that reaction one more time, but I want to scale it up a little bit and go with a bigger test tube, right? Because bigger is always better. So again, I'm going to collect some hydrogen gas. It is still bubbling away pretty well here. And as a little side note, I can feel that the flask is warm, right? This is an exothermic reaction. It's not as exothermic as the lithium water reaction that also makes hydrogen, but I can tell there's definitely some chemical change going on here, and it is releasing some energy. So I'm going to go ahead and let that sit for about 5 minutes. get my timer going on my watch. We'll take a look at the second reaction, the combustion reaction of hydrogen and oxygen. So again, we're going to try to represent the equation symbolically and with a diagram. It tells us that hydrogen gas reacts with oxygen gas. So again, we have H2 gas with oxygen gas. And it reminds us with our hint that oxygen is also a diatomic molecule. So an oxygen atom has 6 valence electrons, unstable as is, but if it gets together with another oxygen and does a double bond, each of them has their octet. So it's O2 gas. And it says we produce water vapor. So we produce H2O. And because it's vapor, it's also a gas. Now, some of that water vapor will condense on the inside of the test tube. We might be able to see that even better with the bigger test tube. Okay, so let's think about balancing this. Let's represent H2 as, again, a diatomic molecule. Oxygen is the same, diatomic. And they need to somehow combine and rearrange to form water. So if you think back to our study of molecular shapes, water is a bent molecule, so I'm going to try to represent it as such, something like this. Okay. And if we just look at our atom totals, we've got 2 hydrogen in the unbalanced equation, 2 hydrogen over in H2O, so that's good. I've got 2 oxygen and only 1 oxygen on the right. So I have to have these combined without any leftovers. Something has to happen to the second oxygen. So the only thing I can do, remember, is multiply these. I can't change the formula. I can't turn it into H2O2 because that's not water anymore. That's actually the formula for hydrogen peroxide. The best I can do is multiply. So I need 2 oxygen, but I have to multiply the whole molecule. So I'm going to draw in a second water molecule here. I'll draw it a little bit differently, kind of rotated, just because I wanted to. No special reason. And now I have 2 water molecules represented on the right-hand side. So that took care of the problem of having 1 oxygen each from the oxygen molecule. But I created a new problem. Now I have 1, 2, 3, 4 hydrogen on the right and only 2 on the left. But I can fix that. Again, I can't change it to H4, and a hydrogen molecule is always H2, but I could double it. And that would look like this. So a second hydrogen molecule gives us now 4 hydrogen, 2 oxygen, and 2 oxygen. So that is our balanced equation. And again, we don't usually write it, but it's implied that we mean 1 O2 molecule here. So one thing to think about too is what's really happening is these bonds are breaking. These bonds are breaking, and these atoms themselves are reforming. So it's kind of like a before picture and an after picture. The 4 hydrogen end up in a different place in a different molecule, but they weren't created, they weren't destroyed, they were just rearranged. All right, so I've got about 30 seconds left on my timer for our ignition of the bigger test tube. So we can see it's still bubbling away there. The amount of zinc, I don't know how well you can see it, it's quite a bit less because, again, the zinc is dissolving into zinc chloride. And when it's ionized, it is aqueous, right? It's soluble in the solution. I want to give that just a couple more seconds. I will say I've done this. This is my 4th time today. The first 2 times it worked beautifully. The 3rd time you could see that water vapor formed, but there was no pop, no ignition. So we'll have to see which way it goes this time. Go ahead and move that out of the way. So you can see the test tube. Here we go. Different tone to it, right? I thought it wasn't going to go, but it did. And you can really see the water vapor that formed as the reaction went to completion. That water vapor that formed in gas form hits the cooler glass and it condenses into little tiny droplets. So that one actually worked pretty well. And again, on the smallest level, what's happening inside the test tube is 2 hydrogen molecules. So 2 hydrogen molecules are reacting with 1 oxygen molecule to make 2 water molecules. Make sure I said that right. Every 2 hydrogen molecules react with 1 oxygen molecule to make 2 water molecules, H2O. All right, so let's look at the next example. We're going to use the same process. This is on your next page. We want to represent the molecules with diagrams. We want to add coefficients, those multipliers. And we want to make sure that all the atoms we start with are converted into product. Okay. All right, so CH4 is methane. Again, thinking back to our study of molecular shapes, methane molecule is tetrahedral. So I'm not going to draw that super accurately, but it's going to look something like this. Our methane molecule. It is combining with oxygen. So this is actually another combustion reaction, burning. Oxygen I can represent this. And they will get converted into CO2, carbon dioxide. And again, thinking back to our study of molecular shapes, carbon dioxide is a linear molecule with the carbon in the middle. And again, we produce water. So that is one of the hallmarks of a combustion reaction, is it involves oxygen, and water is almost always one of the products. So my water molecule, again, is a bent molecule. I'll try to show that somewhat accurately, like that. So you'll get to a point where you don't necessarily need to draw the pictures to prove your answer. When you do that, I would recommend tallying up your element totals on each side. So what I mean by that is I'm going to tally up the carbon total, the hydrogen total, and the oxygen total on both sides, because the number of atoms of each element should be conserved. Because I'm not creating atoms, I'm not destroying atoms, I am simply rearranging atoms. So here, if I look at everything, I only have 1 carbon. I've got 1, 2, 3, 4 hydrogen, and 2 oxygen in the unbalanced equation. I've got 1 carbon, 2 hydrogen, and a grand total of 1, 2, 3 oxygen. So carbon is good, hydrogen is not balanced, oxygen is not balanced. I think the easiest route to go is to take care of the hydrogen, only 2 compared to 4. Again, I can't turn this into H4O. That would be a completely non-existent molecule. It's got to be H2O. But I can double it. And by doubling it, I've made a second water molecule in my diagram as well. So now by doubling the water molecule, my hydrogen total is now 4. Cross out the 2. Now I have 4. The other thing that did, because it doubled the entire molecule, is my oxygen total has now changed. It's no longer 3, it's 1, 2, 3, 4. So I couldn't help but also affect the oxygen total by doubling the water molecule total. So rechecking, I've got 1 carbon, 4 hydrogen, 2 oxygen, 4 oxygen. So I need to get more oxygen on this side. Again, I can't just make this subscript a 4, but I can double my number of O2 molecules. So in my diagram, I'm going to add a second O2 oxygen molecule. Now I'm balanced. Okay. And that's the general process. Kind of draw the pictures for now. You won't always have to draw the pictures, but at least to start, or if you're kind of a visual thinker, the diagrams can help a lot. Look at your element totals. Wherever you're unbalanced, we need to add multipliers and try to get those element totals equal in the reactant side of the equation and the product side of the equation.